Yes, good afternoon. Let's start the class.
Good afternoon, sir.
Okay. My voice is audible to you?
Yes, sir.
Yes, sir.
Right. Coming to continuation of the previous class. Here we stopped. Yeah. Functional group identifications. Type and nature of functional group present in each. Okay. The type and nature of functional group depends on the type of elements present in the molecular formula. Yeah. Suppose this is the molecular formula. This is the molecular formula. Whenever we are considering this molecular formula, this is the molecular formula of morphine. Now we see this here. The other than the carbon and hydrogen, oxygen and nitrogen are there. The nitrogen may be the part of cycle. Therefore, it is the part in the nitrogen is the part of heterocyclic. Nitrogen is the part of heterocyclic. And oxygen, whether here oxygen is there, three oxygens are there. These three oxygens maybe is in the form of different oxygen functional groups. Okay. And first coming to identification and nature of oxygen. This identification and nature of oxygen. This oxygen may exist in the any organic molecule, maybe in the hydroxy form or in the form of ether form. This is hydroxy. It is in ether form. It is in aldehyde form. It is in keto form. It is also called an oxo. It is in the form of carboxylic acid. It is in the form of ester. Sometimes the oxygen and nitrogen combined together, they generate amides. Right. Now, in these forms, it may be in the hydroxy form, it is maybe in the ether form, aldehyde, ketone, or carboxylic acid, ester, or amide. Now, these functional groups are present. How these functional groups are identified? First, we come into hydroxy group. This is the hydroxy group. Hydroxy group may exist in the form of simple aliphatic OH, that is simple alcohols, or it is maybe in the phenolic OH, that is the OH and phenol, that is in the phenols. How these hydroxy groups are identified? Then first you coming to simple OH, not only phenolic, when alcoholic OH is present, ROH. Now this ROH is treated with, this is the acetic anhydride, or it may be acetyl chloride. Is treating with alcohol that leads to the formation of an ester. Therefore, whenever you are treating the natural products with acetic anhydride or acetyl chloride, that leads to the formation of an ester that indicates that the presence of OH group, that is aliphatic OH group, right? Not only aliphatic OH, phenolic OH is also, these are the general reactions for the OH, whether it may be alcoholic or phenolic. Now, see another one. If you take, suppose the first one, you take any product, simple alcohol, like in cholesterol. In cholesterol, there is a simple cholesterol. The cholesterol is having OH. It is in the form of ring. Okay. This is the additional structure. It is having OH. It is treated with acetic anhydride or acetyl chloride. Acetic anhydride or acetic chloride in acetyl chloride in pyridine. That leads to the formation of an ester. This OH is reacting with C double bond O, CH. Right. Suppose you take the phenol. This is the aromatic compound. Reacts with an acetyl chloride or acetic anhydride. Right. Twice. That leads to the formation of phenyl acetate is the product. Right. Therefore, any alcoholic group or phenolic group easily identified by treating the acetic anhydride or acetyl chloride in pyridine. That leads to the formation of ester. When any natural product it produces the acetic and it produces the ester, and that is especially acetate ester derivative with a natural product by reacting with acetic anhydride and acetyl chloride. That indicates the presence of OH. That is, it may be alcoholic OH or phenolic OH. Similarly, this is the benzoyl chloride in alkali. Alkali means we are using KOH or sodium hydroxide. Then that leads to the formation of benzoate. The benzoate is generated, right? The formation of benzoate or formation of acetate indicates that the molecule are natural products existing with one OH group, right? It is the primary detection of OH. Now, coming to nature of alcoholic OH. Suppose the OH is alcoholic OH. Now, the alcoholic OH may exist in three forms. The alcoholic OH is existing in three forms. The one is the primary alcohol. That is, aliphatic alcohol may exist in three forms. Secondary alcohol, tertiary alcohol. In primary alcohol means, suppose CH2OH. This is the primary alcohol. Therefore, the OH is attached with the primary carbon. Right? Now, if it is attached with secondary carbon, CH3, this is secondary alcohol. Tertiary alcohol. Primary alcohol, tertiary alcohol, and secondary alcohol. Right? Suppose the given compound or isolated compound of natural products may contain primary alcohol. Whenever it is an oxidation, that leads to the formation of an aldehyde. That leads to the formation of, suppose, if it is an oxidation, that leads to the formation of R, CH2, CH4. Suppose if it is an over-oxidation, that R, CH2, the aldehyde is converting into carboxylic. A simple primary monocarboxylic acid is generated. For example, this is the primary. This primary alcohol on oxidation, it leads to the formation of aldehyde. That aldehyde on over-oxidation leads to the formation of monocarboxylic acid. This is the only one product. Only one product is generated. This is the example for the primary alcohol on oxidation leads to the formation of aldehyde and carboxylic acid. Now coming to secondary alcohol. This is the secondary alcohol RH, RCH, ROH. This is a secondary alcohol. This secondary alcohol is on oxidation leads to the first it is converting into ketone. On over oxidation, this will be broken down. The carbon R bond will be broken down. Therefore, it is converting into two different sized carboxylic acid. Two carboxylic acids are generated. Two carboxylic acids are generated. Okay. When primary alcohol is an oxidation, it leads to the formation of monocarboxylic. One carboxylic acid is generated. If it is a secondary carboxylic acid, that is on oxidation, first it is converting into ketone, later it is converting into two carboxylic acid. Now coming to tertiary alcohol. Now this is the tertiary alcohol. In this tertiary alcohol on oxidation, it is a normal oxidation or moderate or slighter conditions. Okay, there is no reaction. First, it is inert towards oxidation, but under drastic conditions, under critical conditions on oxidation, it leads to formation of 3-carboxylic acid. Therefore, we can easily understand that tertiary carboxylic acid will not undergo oxidation simply. It requires a special condition. Under special condition, it is undergoing oxidation that leads to the formation of carboxylic acid. That carboxylic acids are 3-carboxylic acids are generated. So you take the primary alcohol, it gives them only 1 carboxylic acid. Secondary gives the 2 carboxylic acid. Tertiary alcohol gives the 3 carboxylic acids. Now, at the same time, the alcohols may be a cyclic alcohol. That means the OH group may be substituted on the ring. Okay, this is the example. Sorry. Yeah, this is the example. Pentanol, cyclopentanol. OH is substituted on the 5-membered ring. Therefore, this kind of cyclic alcohol on oxidation, first it is converting into cyclic ketone. The cyclic ketone, cyclopentanone, is generated. The cyclopentanone on over oxidation that leads to formation of the CC bond cleavage that leads to formation of dicarboxylic acid. This is the dicarboxylic. Only a single compound, but dioic acid or dicarboxylic acid is generated. This is also called dioic acid. Dioic acid is generated. Okay, when the given OHs or the isolated compound may have the cyclic alcohol that leads to the formation of dioic acid. It is already seen in the case where we have seen in the case of camphor. In the camphor, the 6-membered ring is attached with the keto group at the adjacent to the methyl group, which is an oxidation. It gives the dicarboxylic acid. Okay, that is the example. Right. Now, nature of phenolic group. All those are explained for the only aliphatic OH group. Whenever the OH group is the aromatic or phenolic OH, how it is identified? It shows the positive test. Whenever we are doing a phenol test, some tests are there. FECL test, Lieberman test, Talin fusion test, okay, azodite test, all are the example for the phenolic OH. Okay. Now here also, some tests are eligible to do the confirming the phenolic OH in the natural products. It shows positive test for all phenol tests like chlorination with alkaline PPCl3, Lieberman, Talin fusion test, right? Azodite test is also useful. Under that, we are going to do the Zerwin-Traub test. This is a special test. It has some importance. The presence and number of functional groups with a active hydrogen, that is OH, COOH, NH, etc., is estimated by Zerwin-Traub method. This method is not only useful with alcohol. This test is extended to whenever the active hydrogen containing functional group like OH group, like COOH, right, or NH. All these functional groups are having active OH. Whenever active OH is present, these functional groups and the number of these functional groups can be estimated by using this method, Zerwin-Traub method. A compound with OH group is reacted with Grignard reagent. Here it is given a Grignard reagent and form the number of moles of and it forms the methane. It forms the methane. The number of moles of methane gas is evolved that is equivalent to the number of OH group present in it. Here, the OH group is there. This is the OH group. This OH group is reacting with the Grignard reagent. This is the Grignard reagent. Right, this Grignard reagent and reaction with alcohol that leads to formation of methane along with ROMGI. ROMGI. That means the hydrogen is replaced with the Mg, magnesium iodide. Alkoxy magnesium iodide. This is alkoxy magnesium iodide. Okay. Now here the suppose only one OH is there, one OH is present. It will generate only one equivalent of methane. Suppose here N OH groups are present. N OH groups are present in the molecule. That leads to formation of N moles of CH4 gas is evolved. Therefore, that is equal to the number of OH groups are equal to the number of moles of CH4 evolved from the reaction. Okay, that is equal. Therefore, by which we can easily find out that the number of OH groups are equal to the number of moles of methane gas is evolved from the Derwent-Roth reaction. Right? Now, coming to phenolic OH. Right. Phenolic OH are already over. All the phenolic tests are applicable for doing. Suppose if we are taking the phenolic compound, already we done the experiment test. Alkaline FeCl3. Take the phenolic group. Phenolic compound, a simple phenol you can still. Whenever it is treated with FeCl3. A deep coloration. A deep, intense deep color. Intense deep color. Suppose the same phenol is doing the Lieberman test, phthalic fusion test, are also giving the red, blue, or violet coloration is general. That indicates the presence of phenolic OH. Okay. Next, coming to carbonyl compound. Suppose the oxygen is in the form of carbonyl compound. First, you take the carbonyl compound. Later, we will move to the ether. Then you take the G-cell method. G-cell method is a specialized method for estimating the number of OCH3 groups. Number of OCH3 groups. Derwent-Roth method, G-cell method is helpful for the estimating the number of OCH3 group present in the alkali. Here, alkalide is the alkalide, a natural product, is heating with hydrogen iodide. Hydrogen iodide. That leads to the formation of whatever the OCH3 present in the alkali is reacting with HI. That leads to the formation of methyl iodide. This methyl iodide is estimated, quantitatively estimated by using the AgNO3. That leads to the formation of silver iodide precipitate. Precipitate is generated. The number of moles of AgI precipitated is equal to the number of methyl iodide generated. Then same, the number of methoxy groups are present. Suppose n number of moles of AgI precipitate. Therefore, n methyl iodide are generated. The same equal to n OCH3 groups are present in the molecule. That means you are taking one equivalent of or 1 mole of alkaloid. That leads to formation of 1 mole of n moles of methyl iodide. That n moles of methyl iodide is reacting with silver nitrate. That leads to the formation of n moles of AgI precipitate. Therefore, that is equal to the n number of OCH3s are present in the molecule. Okay, here the sentence is the number of moles of AgI deposited is equal to the number of OCH3 groups present in it. Right. Next. This is very important for estimating the number of OCH3 groups in a alkali. Next, test for carbonyl group. Carbonyls are, you know that, aldehydes and carbonyl compounds are aldehydes and ketones. Aldehydes and ketones. Okay. Aldehyde functionality is suppose R, CH4, or you can also write like this R, C double bond OH. Or ketone. The ketone is RCOR, or we can also write RC double bond OR. Right. Now, a general tests are there for finding out the carbonyl group. That means that this is the carbonyl group. C double bond oxo group is the carbonyl group. The aldehyde or ketone, this is the general. Right. Now, this can be reacted with the three reagents. It is reacting with 2,4-DNP. That leads to formation of 2,4-dinitrophenyl hydrazone is generated. Suppose this is the 2,4-DNP. This is the 2,4-DNP. Whenever it is reacting with an aldehyde or ketone, it leads to formation of 2,4-dinitrophenyl hydrazone derivative is generated. Now, it is also reacting with an oxime. Oxime can react with the both aldehyde and ketone, that leads to formation of aldoxime and ketone. This is the aldoxime and a ketoxime. Right. Aldoxime and ketoxime. Both will be both carbonyl compounds will be generated the oxime derivative. Next, semi-carbazide. Semi-carbazide is like this. NH2, NH, NH2. This is the semi-carbazide, right? Whenever you are treating the semi-carbazide with the carbonyl compound, it leads to formation of semi-carbazone derivative. Suppose you take an aldehyde or an aldehyde, NHC double bond O. Aldo semi-carbazone derivative. At the same time, if it is a ketone, that leads to formation of keto semi-carbazone derivative. Okay. Therefore, these are the common reactions to identify the carbonyl group present in the alkaloid. Next, if a specific test for the aldehyde. If you take the aldehyde group, if it is present in the natural product, you need to test with tolerance reagent or Paling's reagent or SCIPS. These are the three reagents are the specifically react with the aldehyde that leads to formation of corresponding reagent. Suppose if it is the tolerance reagent, that is silver oxide, ammonical silver oxide, that leads to the formation of a silver deposit or silver precipitate at the bottom of the test tube with the aldehyde. A silver mirror is generated with the tolerance. When you come into the failing solution is a mixture of two reagents. One is the failing A and failing B. That is copper sulfate and tartaric acid solution, sodium salt or tartaric acid solution. Then whenever we are mixing together, it leads to the formation of a red precipitate. Okay, SCIPS reagent. This is the para-rosanilide. This para-rosanilide reacting with the aldehyde that leads to formation of a pink coloration of the solution. Okay, when these colorations of these precipitates are generated, that indicates that the aldehyde group is present in the natural product. Now coming to the ketone. When ketones are, all the aldehyde tests are given negative. Suppose 2,4-DNP gives the precipitate, yellow or orange, yellow color precipitate or orange red color precipitate is generated, that indicates the presence of a carbonyl group. But whenever we are doing the aldehyde test, all the aldehyde tests are negative. No precipitate with the tolerance reagent, no precipitate with the failing test, no precipitate with the skip space, or no coloration of the with the skip space, right? Skip solution. Then aldehyde group is absent. Then the carbonyl compound should be a ketone, right? After ketone is identified, whether the ketone is a aromatic ketone or methyl ketone, whenever it is, suppose if it is a methyl ketone, that means the ketone at the alpha position, the CH2 group is there, that is called methyl ketone. That methyl ketone is uh, identified by iodoform text. Iodoform text. Okay, or otherwise, if it is the aromatic ketone, that aromatic ketone is identified by the sodium metal fusion with the naphtha mix. Whenever the keto is treating with the sodium metal and the naphtha mix, it gives a red or green coloration around the sodium metal, molten sodium metal. That indicates the aromatic ketone. In this way, we can identify the aldehyde and the ketone. Next, test for carboxylic acid. These are all the carboxylic acids and esters. Carboxylic acids are the oxygen functional groups. Okay, these oxygen functional group carboxylic acids can be identified by simply ester formation or salt formation with the alkali solution. Right. Next, determination of the nature of nitrogen. Here, the nitrogen may exist. Nitrogen may exist in the form of amines, amides, nitro, nitroso, nitrile, isonitrile. Okay, in all these forms, amino group is very much important because amino again it exists in the form of primary amine and secondary amine. Tertiary amine. In some cases, quaternary amine also appear. Right. RNH2, RNH, R the tertiary amine and quaternary. Just a minute.
Sir, is there any technical problem, sir?
Just a minute, just a minute. I'm going to start the secondary class. Okay. For the other counselor, I'm starting the secondary class. Just 2 minutes.
It's okay, sir.
Yeah, okay. Now this is the amino group may exist is in the form of primary amine, secondary amine, tertiary amine, or quaternary. Now, when the test for amine, whether it is the primary, secondary, tertiary, quaternary amine not required, it is a salt formation. Okay, primary amine. Suppose the amine it is the form of primary or secondary, H2 or NH form. Whenever it is reacting with acetic anhydride, right, or acetyl chloride in presence of pyridine, that leads to formation of amide. The formation of amide from the natural product indicates the presence of amino. Okay, there is a free H is present on nitrogen. Free H is present on nitrogen. Right. Now, coming to secondary amine, there are single test we can easily recognize or differentiate the amine whether it is the primary, secondary, tertiary. That is treating with nitrous acid in the cold condition, that is 0 to 6 degrees Celsius. The primary amine will convert into corresponding alcohol and evolve the nitrogen gas. If it is the secondary amine, that leads to the formation of nitroso compound. The nitroso compound is generated. If it is the tertiary amine, it will not react with the tertiary amine. That nitrous acid will not react with the tertiary amine. This simple reaction with the nitrous acid is easily differentiate the primary, secondary, and tertiary amine. Reaction with methyl iodide. So, look at here. Amine is reacting with methyl iodide that leads to formation of iodo-quaternary ammonium salt. That is the final product. That is ultimately that is the final. Suppose the alkyl amine is reacting with methyl iodide. First, it produces the N-methyl. Only N-methyl amine is generated. It is again reacted with another molecule of methyl iodide that leads to the formation of NN dimethyl. This is the NN dimethyl amine is generated. Again, this NN dimethyl amine is reacting with another mole of methyl iodide that leads to the formation of NNN trimethyl alkyl amine. It is the iodinium salt. Iodinium salt is also called as quaternary ammonium salt. Quaternary ammonium salt. Right. Suppose if you take the primary amine, it requires 3 equivalents of methyl iodide to produce the quaternary ammonium salt. If you take the secondary amine, it requires the 2 equivalents of methyl iodide to produce the quaternary ammonium salt. If you take the tertiary amine, it requires only 1 equivalent of methyl iodide is required to produce the quaternary salt. Okay. Based on this, number of moles of methyl iodide utilized by the natural product to produce the quaternary ammonium salt is equal to the kind of primary amine. If it is consumes the 3 methyl iodides, 3 equivalents of methyl iodide, that is equal to the primary amine. If it consumes 2 methyl iodides for the formation of quaternary ammonium salt, that is equal to the secondary amine. If it is only consumes 1 mole of or 1 equivalent of methyl iodide, that indicates the presence of tertiary amine. Right? Identification of NCH3 and NN dimethyl amine groups. N-methyl group, methylamine group, and NN-dimethyl amine group. It is treating with a strong base. Look at here. This is the N-methyl fragment, N-methylamine fragment, present in the natural product. It is treating with potassium hydroxide in presence of sodamide. That is the formation of a primary methanamine in general. Primary methanamine. What's happening whenever it is treating with potassium hydroxide and sodamide? That means the formation of these bonds will be broken down and added one hydrogen. Breaking up each bond leads to the addition of one hydrogen to the nitrogen. That means the formation of methanamine is generated. At the same time, you take the NN dimethylamine. This is the NN dimethylamine fragment is present in the natural product that is reacting with potassium hydroxide and sodamide. That leads to formation of NN dimethylamine is generated. That is the final product. It's the final product. NN dimethylamine is the final product. What's happening whenever breaking of this bond, the hydrogen is added here, then the remaining fragment is separated as separate compound. That means the formation of NN dimethyl product. Therefore, simply, whenever you are treating the natural products with the strong base like potassium hydroxide in presence of sodamide, that leads to the formation of methanamine indicates that one methanamine group is N-methyl amine group is present in the molecule. Suppose 2 methanamine molecules are generated, that indicates the presence of 2 N-methyl amine groups are present. At the same time, if it is producing dimethylamine, that indicates that the natural products may existing with a fragment of NN dimethylamine group. If it produces the one fragment. If it is producing 2 moles of or 2 equivalents of dimethylamine, that indicates the presence of 2 fragments of NN dimethylamine fragment. Okay. This is the identification of NCH3 and NN dimethyl group, methylamine groups. Next, Herjig-Meyer method. This Herjig-Meyer method is estimating how many number of NCH3 groups present in the natural product. In this reaction, it is very much similar to Diesel, I think Diesel method. Yeah, Diesel method. Diesel method is applicable for the OCH3 group. And our OCH3 group is present, we are applying the Diesel method. Suppose the NCH3 groups are present, we are applying the Herjig-Meyer method. But both the methods are using the same reagent, hydrogen iodide. Hydrogen iodide is treating with this N-methyl amine group. That means the formation of a methyl iodide. That methyl iodide further treats with the AgNO3. That leads to the formation of AgI precipitation. The number of moles of AgI deposited from the natural products is equal to the number of NCH3 groups present in the natural product. Okay, this Herjig-Meyer method is also important. These two, Diesel method, Herjig-Meyer method. Next, the first one is the Derwent method. These two methods are important. These two methods may ask in the short question. Right. Amides and lactams. Alkalides with amides and lactam. Amide is the acyclic form. It is the cyclic. It is the lactam. Right. It is an hydrolysis. It leads to the formation of carboxylic acid. Or if it is the amides, it leads to the formation of amines or the major products. Lactams are the cyclic esters are generating the carboxylic acids. If it is the cyclic amide, that is the lactam. If it is the ester is the cyclic ester, that is called a lactone. If it is the amide is the cyclic ester, that is called lactam. This lactam is an hydrolysis that leads to the formation of That is the formation of carboxylic amino carboxylic acid derivative. That is indicating the lactam presence, lactam fragment or lactam functional group presence in the natural product. And the second thing, whenever you are taking the acyclic amide group is present in the alkyd, which is on treating with the hydrolysis, it leads to the formation of two products. One is the carboxylic acid and another one is the amide. Both products will be generated. But here the difference you need to understand. Amide is the acyclic form. Whenever it is an hydrolysis, it leads to the formation of carboxylic acid and amide are the products. Whenever you are considering lactam, the lactam, suppose this is the lactam. You get here. I'm taking this is as the lactam. Taken N. Now, whenever you are on hydrolysis, you are subjected to hydrolysis. The hydrogen is added here, the OH is added here. Now, the product is only one compound, that is amino acid. Amino acid will be generated. There is the difference between the lactam and simple amide, right? Next, detection of the ring. The rings are detection by using the simple formula double bond equivalence. Based on the double bond equivalence, we can find out the presence of the number of rings in the molecule. Here the double bond equivalence is equal to, here the double bond equivalence calculation involves a formula, right? This is the double bond equivalence, DBE is equal to the number of carbons present in the molecular formula, minus number of hydrogen by 2, number of hydrogens by 2, minus this is the number of carbons, minus number of hydrogens by 2, minus number of halogens by 2, plus number of nitrogens by 2 plus 1. This is the part. Number of carbons minus number of hydrogens by 2 minus number of halogens by 2 plus number of nitrogens by 2 plus 1. This is the part, right? Now, this is the example for determining the number of rings present. Okay, nature of ring and number of rings present in it. Double bond equivalence is equal to how many? It is the molecular formula. How many number of carbons are there? 17 carbons and 18 hydrogens, 1 nitrogen, and 3 oxygen. 3 oxygen. Now, 17 hydrogens, 17 carbons, number of carbons minus number of hydrogens by 2. Is 19 by 2 is equal to 9.5, right? 19.5 by 2 minus no halogens, and minus here the plus, not minus, the plus, right? Number of nitrogens by 2. Only one number of nitrogens are there, 1 by 2 plus 1. Therefore, the 17 minus 19.2 plus 0.5 plus 1. Then 17 minus 9 plus 1. 17 minus 9, 8 plus 1. Therefore, the result is 9. In that 9, double bond equivalence is 9. How many double bonds are there in this? Look at here. From the molecule, 1 double bond, 2, 3, 4 double bonds are there. It's the 4 double bonds. 4 double bonds. Therefore, the 7 minus the number of rings is equal to. The number of rings is equal to 9 minus 4. That is the result is 5. Total number of rings are 5. Look at here. How many rings? This is 1, 2, 3, 4, and 5. This is the 6 member ring also. Right. Total 5 rings are there. Okay. By using this formula, we can find out the number of rings present in the molecule. That is double bond equivalence. After calculating the double bond equivalence, we deduct the number of double bonds. That results in the number of rings present in the molecule. Next, detects Detection of the rings based on the molecular formula. This is already given in the case of terpenoids. By using the general formulas, CnH2n, that is indicated the monocyclic compound, CnH2n minus 2 dicyclic or bicyclic compound, CnH2n minus 4 that indicates the tricyclic, and CnH2n minus 6 that is equal to tetracyclic. Whenever we are detecting the number of 2n minus, increasing the number 2, that is 2n minus 8 that is equal to pentacyclic, 2n minus 10 that indicates the hexacyclic, like that. Right? We are already worked on this formula. We have succeeded also in the structural stuff, camphor. Okay. Next, chemical degradation experiment. This chemical degradation experiments, we are by you. What is the degradation? I have already given the definition in the previous. Degradation is the dividing the or bisecting the molecule into smaller fragments, by which we can understand the molecular composition or molecular structure. Right. Here, the determination of the nature of heterocyclics by using 4 kinds of degradation experiment. One is Hoffman exhaustive methylation. It is also called HEM method, HEM degradation. Hoffman exhaustive methylation or HEM degradation. And the second one is MD degradation, EMDE, MD degradation. And the third one is Van Braun degradation, Van Braun degradation. Fourth one is reductive degradation. By using some reducing reagents, reduction reagents, we can apply the reduction reaction on that molecule. We can find out the nature of the heterocycle. Okay. Now, first coming to the HEM method, Hoffman exhaustive methylation. In the Hoffman exhaustive methylation, the heteroaromatic ring cannot be subject to HEM. It is first reduced to corresponding saturated heterocycle by the hydrogenation using catalytic hydrogenation. We are using nickel hydrogenation. Nickel is the catalyst. Catalytic hydrogenation is applied on the aromatic heterocyclic. That aromatic heterocyclic is converting into corresponding saturated heterocyclic. That is, pyridine is converting into. Suppose here we are a pyridine derivative. We are considering a pyridine derivative is considered. This pyridine derivative is subject to catalytic hydrogenation that leads to the formation of a saturated heterocycle. This is pyridine derivative, which is treating with the methyl iodide. It is the secondary amine. Pyridine contains the amino group is nitrogen is existing in the form of secondary amine. The secondary amine is converting into quaternary ammonium salt by treating with methyl iodide in presence of silver hydroxide. Therefore, it leads to the formation of a quaternary ammonium salt of hydroxide is generated. Then again, it is treating with methyl iodide. Again, it is treating with methyl iodide. Then it will open up the ring. What's happening? There is a beta hydrogen here. This is alpha position. This is beta position. Beta hydrogen and carbon hydrogen bond pair of electrons is donated to the ring. At the same time, nitrogen alpha carbon bond will be broken up. That leads to the formation of an unsaturation, and it will open up. Later, again you treat it with the another molecule of methyl iodide. Another molecule of methyl iodide in silver hydroxide that leads to the formation of another quaternary ammonium salt. After formation of quaternary ammonium salt, again the same beta carbon hydrogen bond is donated to the alpha carbon. At the same time, alpha carbon nitrogen bond will be broken. That leads to the formation of N-trimethylamine is generated along with this fragment is generated. What is this fragment? We called it as number, give the number 1, 2, 3, 4, 5. 1, 5. Dipentadiene or pentadiene. 1, 5 pentadiene. 1, pentadiene derivative is generated. The formation of 1, 5 pentadiene indicates that the size of the heterocyclic is 6 members. The size of the heterocyclic is 6 member. That may be a pyridine derivative or piperidine derivative. Right. Similarly, Hoffman exerts to methylation of like isoquinoline and quinoline gives this pattern. We can do that. After formation of this quaternary ammonium salt, that leads the formation of this derivative. Styrene derivative is generated. The same way, quinoline is under subjecting to hem method or often exists in methylation. First it generates the quaternary ammonium salt. Later it is generated to the aniline and ortho substituted allyl substituted. This is the allyl fragment, not allyl. Allyl, ortho allyl, NN dimethyl, aniline derivative is generated. NN dimethyl derivative is generated. Okay, this hem is clearly differentiated the quinoline and isoquinoline. If it is isoquinoline, this gives this kind of product. If it is a quinoline, it gives the aniline product. Okay. Now, here the only reagent is first in the Hoffman exhaustive methylation, aromatic ring is converting into fully saturated ring. That fully saturated ring is treated with the methyl iodine in the silver hydroxide. That leads to formation of quaternary ammonium salt. Further, it is treating with the methyl iodide with the silver hydroxide. That leads to the formation of open up that saturated ring. That leads to the formation of acyclic compound. The formation of based on by observing that acyclic compound, you can find out the nature and size of the ring. Right. Next, coming to MD's method. In this MD method, instead of vanillin nickel and hydrogen pressure, he is using platinum and hydrogen pressure. Platinum is the catalyst. In presence of platinum, hydrogen gas is passing through the hydrogen pressure is applied on the molecule that leads to the fully saturated compound. Okay, right. This degradation is helpful when beta hydrogens are absent. Suppose in the MD's method, it requires the beta hydrogen. Beta hydrogen should be free. That hydrogen should be involved in the Hime method that leads to the formation of a double bond by the elimination of quaternary ammonium nitrogen from the ring. That is the end. That is reason for the formation of end products in the hem. But in this case, whenever the beta hydrogen is absent, this MD method will be applied. But in the MD method is also, we cannot apply the aromatic ring. Again, aromatic ring will not apply. Here also look at here. A quaternary ammonium salt of the ring will be fully saturated, except these 2 carbons. These 4 carbons are fully saturated. These 4 carbons are 4 elements. 2 carbons and 3 carbons and nitrogens are fully saturated. Therefore, it is treated with the hydrogen pressure in presence of platinum or sodium metal in liquid ammonia. That leads to open up the alpha bond. This alpha bond will be broken down. That leads to the formation of this product. Okay, this product is generated. After this product generation, it is reacting with hydrogen iodide. That leads to the form hydrogen iodide in presence of methyl iodide and silver hydroxide. That leads to formation of again quaternary ammonium salt. That quaternary ammonium salt further treated with the silver iodide. Look at here. Just a minute. Yeah. Isoquinoline. Isoquinoline. Okay. I will rewrite again. Please follow this. I will give it clear. This is isoquinoline. Yeah. Now this isoquinoline is treated with the sodium metal in ethanol, the pitch reduction. That leads to the formation of fully saturated nitrogen heterocyclic in the isoquinoline. right? Which is treated with NH. This one, NH. This is treated with methyl iodide in silver hydroxide. That gives the formation of CH3, CH3. The positive charge is up here. This positive charge is stabilized by this iodine, imines. That iodine salt of quaternary ammonium salt, right? Now, whenever we are applying MD's method, it is treated with sodium mercury in ethanol. Sodium mercury in ethanol. That leads to the cleavage of this alpha bond. That leads to cleavage of this alpha bond. CH3 Okay, the presence of this NCH3 can be estimated. In the previously, we are applying one method, that is treating with sodamide and potassium hydroxide. Based on that reaction, we can estimate the how many number of NN dimethyl amine group is there. This kind of functional group can be estimated by treating with the potassium hydroxide and sodamide. Okay, then again it is treating with methyl iodide and silver hydroxide. Again, we are applying here M. A part of MD is M. Now again it leads to the generation of positive charge, right? Now at the beta hydrogen,
Sir, you are in mute.
Sir, it's not audible. Sir, are you there?
Okay, right. Now audible it is? Is it audible now?
Yes, sir.
Yeah. Okay. Actually, the equation given is here is wrong. Okay. You take it down. Given one is given. I'm taking the a quaternary ammonium salt of reduced quinoline. This is the quinoline. Here the aromatic ring is reduced to saturated one. Then at the same time, I'm applying MDS method and HEM method. Often exists methylation method and MDS method. Okay. And the HEM method, the product is like this. The degradation stops here. The degradation experiment is stops here. There is no complete detachment of nitrogen fragment. But whenever we are applying MDS method, the product will be generated first. First one, this one is okay. There is a breakage of this bond in the MDS method. Then it leads to the formation of this product, right? This product is generated. Whenever generation of this product, we are applying again HEM method, Hoffman exhaustive methylation method. Then it leads to the formation of this product. Now look at here, the difference between the direct M method, that is Hoffman exhaustive methylation method, and this is the product of MD's product. This one is MD's product. This is the HEM product. Now we can clearly understand that what are the products are generated in the HEM degradation and what are the products generated in the MDC. Okay. Next one is Van Braun degradation method. This Van Braun degradation is of two types. The first one is Van Braun cyanogen bromide degradation experiment. Here we are using cyanogen bromide. We are using cyanogen bromide in the Van Braun method. If we are using cyanogen bromide, that is called as Van Braun cyanogen bromide degradation experiment. In this N-methyl amino isoquinoline derivative is subjected to Van Braun degradation that leads to the formation of this product. At the alpha position or benzylic position will be brominated. This bond will be broken down that leads to the formation of N-methyl amino product is generated. And the second one, a simple Van Braun method for the secondary cyclic amines. Secondary cyclic amine, this is the secondary cyclic amine, but it is the amino group is tertiary one. Here the cyclic group, this amino nitrogen is exist in the form of tertiary, but here the nitrogen is exist in the form of secondary amino, right? It is treated with benzyl chloride in presence of sodium chloride, sodium hydroxide, that leads to the formation of N-benzylation is takes place. N-benzyl derivative is generated. This N-benzyl derivative is treated with PBr3 in bromine. PBr3 in bromine that leads to the formation of cyanobromide or bromine benzene nitrile. At the same time, the cleavage of this bond and this bond will be takes place. At the same time, attachment of the bromine at the two alpha positions of nitrogen is taken. Then it leads to the formation of dibromo product. Suppose if it is a pyridine derivative 1, 2, 3, 4, 5, 1, 5 dibromo pentane derivative is generated. Pentane derivative is generated. Right? Okay. First addition on the bromine takes place here. Dibromo product is generated. Whenever it is undergoing cleavage, A simple, we can call it as this bond will be bond pair is generated here, right? This bromine is moving to here. At the same time, this bond pair, CN bond pair is moving to here. This bond pair of this bromine is moving to here. Then that leads to the formation of this bond. This is Van Braun degradation. This is one kind of Van Braun cyanogen bromide degradation experiment. This is second one is Van Braun benzoyl chloride degradation experiment. These are the two experiments, two degradation experiments are helpful to know about the size of the ring present in the alkaloid system. Now coming to last one, total degradation. Yeah. Reductive degradation. Just a minute. Next, reductive degradation of alkaloids. Last one, fourth one it is. Reductive degradation of alkaloids. The first one, alkaloids on heating with hydrogen iodide at 200 to 300 degrees centigrade undergoes reductive cleavage of CN bond. It results the removal of nitrogen as ammonia. Like suppose if you take the pyridine, this can directly, the pyridine aromatic system can directly apply the reductive degradation experiment when it is treated with hydrogen iodide at 200 to 300 degrees centigrade. Therefore, this nitro group is eliminated as ammonia gas, and the remaining compound fully reduced to saturated one. Then that leads to the formation of a simple pentane molecule. That is the reductive degradation with the hydrogen iodide. This is one experiment. And secondary, zinc dust reduction. The zinc dust reduction, if you look into here, you take the quinine. Quinine is a quinoline derivative. So CH3.
Sir, in between the reductive bonds are CC and CO, right?
Where? What you are asking?
Zinc dusting.
Yeah, zinc dust reduction.
The reductive bonds are CC and CO, right? Sir, I'm talking bond cleavage.
Just leave it. Here in the degradation experiment, reduction is different from the normal reduction reaction. Okay. Here the reduction is applied in the drastic conditions. At the drastic conditions, that means at maximum temperatures, maximum pressures we are applied. That leads to the formation of a simple known product. That is the use of degradation experiment. Here, whenever the quinine is subjected to zinc dust reductive degradation, that is only generated a pure quinoline. That means it reduces this to this bond, C bond, and OCH3 C bond, oxygen carbon bond will be reduced. only this will be detached from the molecule, right? That means the zinc reduction will give the heterocyclic separated from the molecule. Next, detection of unsaturation. Detection of unsaturation is already discussed. Okay. Next, oxidation of alkaloids. Oxidation of alkaloids is also important. Various oxidation reagents generally used for the selective oxidation or oxidative degradation. Already oxidative degradation experiments seen in the terpenoids, in the alpha terpenol or in the camphor also we see in that oxidative degradation, right? The same kind of experiment can also use it in the alkaloids also. Therefore, various oxidative reagents are used for the selective oxidation degradation or for degradation studies. The oxidation reagents are broadly four types. Oxidation degradation experiments are divided into four types. Four types of, yes, four types of
mild oxidation, moderate.
yeah. Four types of oxidative degradation. In that, the first one is mild oxidation.
Moderate oxidation.
In this mild oxidation, generally we are using hydrogen peroxide, ozone, iodine in methanol, and alkaline potassium ferricyanide. Like reagents can be used for getting the oxidative product, degradation product. And the second one, moderate oxidation.
Alkalines.
Yeah. In this moderate oxidation, we are going to use acidic or alkaline KMnO4, chromic oxide in acetic acid. Like, or you can also DMSO, GCC, like moderate to oxidation reagents can be silver carbonate is also used. Silver carbonate can also use it for the oxidation. Next, third one, vigorous oxidation. Vigorous oxidation. In this vigorous oxidation, K2Cr2O7 in H2SO4 or chromic oxide in H2SO4, concentrate HNO3 or fuming HNO3. And also oleum. All these and MnO2. All these are used for the vigorous oxidation. And the last one, fourth one, here I am going to write. Fourth one, degradative dehydrogenation.
Degradative dehydrogenation.
Degradative dehydrogenation. Here the alkali is treated with the different reagents like sulfur, heating with sulfur, heating with selenium, or heating with bromine.
Pyridine, quinoline.
Right. These are generating hydrogens are eliminated and heteroaromatic rings will be generated. Suppose if any saturated ring containing natural products are isolated from the plant, whenever we are treating these those with sulfur or selenium or bromine, those are aromatized. Aromat, it completely fills the aromaticity of the ring system that leads to the formation of aromatic rings are generated, like pyridine, phenolene, isoquinoline products are generated, right? These are the degradative dehydrogenation method, right? These are the four types of oxidation or oxidative degradations are available for the alkaloid. Yes, this is about the general methods of structure determination of alkaloids. Okay, you go through it. If you have any doubts, whenever you are reading it, then ask me. I will clarify in the next class. Okay.
Okay, sir.
Now I am going to close the session.
Okay, sir. Thank you, sir.
Sir, any other class is there, sir, now?
4 classes over, na?
Yeah.
Okay.
Thank you, sir.
Already 4 classes over, na? You are ready to 5th class?
So what about mathematics classes, sir?
How many classes you are completed?
No, mathematics, no class is no, sir.
No. Already 4 classes are over.
Yes, sir. Yes.
Mathematics, sir.
Yes.
But I didn't get any information regarding the mathematics classes, sir.
Mathematics classes are regularly
On Sunday, sir.
completed. Sunday and Saturdays.
Yes. 3:30 to 4:30 session.
It's already completed.
But physical chemistry only not took, no, sir.
Monday, you need to follow regularly, sir. Okay.
So it is coming in the
All
Telegram
the
group only, no,
classes
sir.
as per the schedules are completed. Only the leftover is the paper 4. Some spectra classes are pending. Those classes will be arranged in the in this week, in the midweek of this coming week, after 6 or 6:30.
Sir, that mathematics classes is available in the YouTube, sir?
Yes, sir, are available. The
Okay, sir.
PRUOU channel 28, I think, or 27.
It's available in YouTube class.
Yes.